Hey everybody, welcome back to NeurosciQ, the best place on YouTube to increase your neuroscience IQ. In today's episode, we're going to be talking about something that might seem like it's straight out of a sci-fi movie. And that something is brain-machine interfaces. Brain-machine interfaces are exactly what they sound like. It's a connection between your brain and a machine so that your brain can control something other than your body. I know, it seems very fictional, something straight out of a movie or a book, but this is something that's being developed right now. So I guess at the end of the day, the future is now. Sit tight, stay tuned, and we'll get to talking about brain-machine interfaces. Let's roll the intro. Like I said before, welcome back to the channel. If you're new to the channel, make sure you hit subscribe right now and turn on post notifications so you can be updated with our weekly neuroscience videos. For now, let's get right into talking about brain-machine interfaces. Now, recently, brain-machine interfaces made the news when a company called Synchron became a part of the FDA's Breakthrough Device Program. This program is a program that offers companies the ability to work closely with the FDA to fast-track development of a device so that it can go from pre-market to the market faster. But these devices need to meet the following criteria. First of all, it must provide more effective treatment or diagnosis for a life-threatening disease or an irreversibly debilitating human disease or condition. And it also must meet one or more of the following. Either it can represent a breakthrough technology, either there are no approved alternatives that exist, it can offer significant advantages over existing approved or cleared alternatives, or the device availability is in the best interest of the patient. Now, let's talk about what the product is that was approved. The product created by Synchron is called the Stent Erode, and this is a device that is implanted in individuals with upper limb paralysis to help them regain the functionality of their limbs and regain functional independence. Patients train their brains to wirelessly control a system, and this is just like Elon Musk's Neuralink or BrainGate. The difference between Stent Erode and other methods are that rather than requiring invasive drilling into the brain, Stent Erode is minimally invasive and enters the brain through blood vessels. So this has been approved by the FDA for the Breakthrough Device Program, which means the company will be able to work faster on developing something that can actually be approved by the FDA and maybe be used in future medical treatments. Let's talk a little bit about how the brain works and then use that to explain how brain-machine interfaces work. First of all, every day when we process information, neurons are firing and different patterns fire in our brain to represent different substrates in the environment. So, for instance, if you want to move your hand up like this, there's a pattern of neural firing in your brain. The same neurons go off, and that controls the movement. Now, it's not just one neuron. We only have 100 billion neurons. I know that's a lot, but for everything we do and all our day-to-day functions, rather than having one job for each neuron, the neurons fire in different patterns that mean different things, and that controls things like movements and emotion. So within the brain, there's not only spatial patterns of neural firing, but also temporal patterns of neural firing as well. So, spatiotemporal patterns are patterns that vary in space or location in the brain, and temporal would be the time of firing and the rate of firing. These groups have been termed voxels, and voxels are just a group of neurons that represent a variable. So, how do brain-machine interfaces work? Brain-machine interfaces are planted on the surface of the brain to hopefully receive signals from the neurons and translate those signals into a computer code to move some sort of machine. Now, early studies were done in monkeys where the electrode is implanted in the brain of a monkey, and they're controlling a cursor on a computer screen to get a reward. Now studies are being done on humans, or human trials are being done to help patients regain things like mobility of limbs or the ability to communicate through a computer. So the main goal of brain-machine interfaces is to restore some sort of lost function. Now, how is this going to work? You can't just implant a translator onto the human's brain and expect it to know what each neuron signal is. It has to be trained first, just like our brain is trained every day. Now, the way that the brain adapts to day-to-day functioning is through a closed-loop system. Not only are we giving output to do something, but our brain is also receiving input from our senses like vision, hearing, or our proprioception, which is the sense of our body's location in space, and our sense of touch. So, for instance, when a baby is learning how to walk, they're going to fall a bunch of times. But eventually the feedback from the body and them learning how they are balanced helps them adjust, and then they adapt the proper neural networks to control their movement and walking. This can also be said for things like learning how to play the piano. If you're learning how to play a song on the piano, you have the feedback of your hands moving, but also if you hit a wrong note, your ear can hear that and you have that auditory feedback that helps adjust the neural firing in the brain to hopefully develop the right pattern of movement. The same complex process needs to be done for brain-machine interfaces. So, to turn a neural activity into an action of a machine, there has to be a decoder that's figuring out what the neurons are saying. Then there's the actuator, which would be the prosthetic limb, and then there is feedback from that limb and from the person's visual system that helps to adjust the movement. What somebody typically is told to do if they receive a brain-machine interface is to think about moving their limb. That would activate the neural pathways that would control the limb, and they link that to the machine so that that specific activity in the brain causes the machine to move. And then adjustments are made to control for velocity and direction and all those sorts of things that we take for granted because our brain just does it naturally. So that's all fine and dandy when you can see the output and the action that is made, for instance, in moving a limb. But a paper published in Nature recently decided to look at using brain-machine interfaces to control internal state and mood in people with anxiety and mood disorders. Now, the problem with this is that mood is hard to put a label on. And if we're trying to regulate somebody's internal state to maybe control for something like depression, which is one of the leading disabilities in America, it's going to be extremely difficult to adjust the reaction within the brain. Because usually with brain-machine interfaces, the first step is to train the decoder, and then the second step is to refine based on closed-loop decoder adaptation. But if we can't see the output and we can't be certain or subjective about the output, then how are we going to adjust the decoder to properly adapt to the neural signals? So basically, at the end of the day, while we are able to do all this sci-fi sort of stuff, we still need to learn more about learning and mood if we want to make accurate brain-machine interfaces to improve people's quality of lives. Now that was just a little tidbit on brain-machine interfaces because of the FDA's recent approval for Synchron. If you want to learn a little bit more about brain-machine interfaces, we also have another episode which will be in the description. You can check that out. And also, make sure you like, comment, and subscribe, and leave any questions you have down below. That's all for today's video. We hope you learned a little bit about the future of neuroscience. and I hope to see you next week on NeurosciQ. Thanks for watching.